Hi everyone, my name is Ryan Julian, and today I'll be presenting efficient adaptation for end-to-end vision-based robotic manipulation. My collaborators are Benjamin Swanson, Sergey Levine, Chelsea Finn, and Karol Hausman. Now the problem we'd like to address today is how can we make robots which continually adapt? End-to-end reinforcement learning has had a lot of success stories, but its deployment story looks a lot like supervised learning. You collect and explore a bunch of data. You learn a model from that data, which you use to act in the environment. Once you're satisfied with that model's performance, you deploy it. And for the most part, that's the end of the story. But the promise of reinforcement learning is that that's not the end of the story. That when you deploy your model and it fails, you can use that failure data to continually create a new and better agent. So we'd like to start finding some simple building blocks that can make that continual learning story a reality. Now here's an example. The robot on the left was trained to grasp any object in its workspace, and it's really good at that. It can grasp a held out set of test objects with 94% success rate. Now, if we take that exact agent and robot and we place a checkerboard pattern behind its workspace, its performance drops to 50% because the agent's now confused. It's never seen this configuration before. What we'd like to do is to take the data from this failure and to use it to boost the performance of the agent back up to the baseline success rate. Our work is an empirical study which shows that you can use a very simple offline fine-tuning procedure and a small amount of data in this new scenario to achieve really strong adaptation results on real-world problems. And furthermore, we show that you can do this without any specialized architectural priors, losses, or algorithms. Now, a really quick preliminary, all the empirical results in this study are based on the QT-opt algorithm and associated grasping architecture for the Q function. QT-opt is very similar to DQN, with a couple modifications made to allow it to use continuous action spaces. And the grasping architecture is very similar to AlexNet. Now, what about this fine-tuning method? Well, honestly, it's barely a method at all. When presented with a new scenario, we use the pre-training Q function to collect a small data set of successes and failures in the new scenario. And then we treat that pre-trained Q function as though you would a supervised learning model, and we fine-tune it offline. We apply new gradient updates using a reduced learning rate. And we change one small detail from regular fine-tuning and supervised learning, which is that rather than using only new data, we use a mixture of the base data and the data from the new scenario. And I want to emphasize that the simplicity of this method is really its strength. We're looking for building blocks for continual learning, and simpler building blocks are better than more complex ones. Now, in our study, we evaluate this method across a panel of 5 different variations that we would expect a robot to see during deployment. We change the objects that it has to grasp. We change the background of the workspace. We degrade the robot's hardware a little bit. We introduce harsh lighting conditions that it's never seen before. And we even change the morphology of the robot itself. Now here's an example of the performance of this method on this checkerboard example I gave you. So on the right, you can see the performance of the robot after fine-tuning. It actually achieves 90% success rate, which is actually better than the baseline grasping performance it started with. Now, another thing we find in our empirical study is that pre-training from reinforcement learning is really essential. On the left, you can see an experiment where rather than using the pre-trained Q function as the basis for fine-tuning, we instead use a Q function that's been preloaded with ImageNet classification features. And then we apply exactly the same fine-tuning procedure I described before. Now we can see that using this procedure, the ImageNet agent does learn some useful skills. It learns to servo and grasp towards objects, for instance, but it fails to learn depth perception from such a small data set that you can access in a fine-tuning setting, and ultimately isn't able to grasp any objects. Now, here's a summary of the results we get using this method for single-step fine-tuning. And as you can see, there's across-the-board improvements in all cases, many of them exceeding the baseline performance. Now, remember, our goal is a building block for continual learning. So we devised this experiment where we repeat this fine-tuning process over and over again, visiting each of the 5 challenge scenarios that we introduced. But this time, each step starts with a fine-tuning model from the previous step, as opposed to the base Q function it explored with. And here's an example of the results from the 5th and final step of this experiment. So this policy was fine-tuned 4 times before it was fine-tuned on this final scenario for the offset gripper. And it still achieves a 91% success rate. So our overall conclusion is that fine-tuning continually isn't any less effective than fine-tuning once. And this is a really great property for a continual learner to have. So now that I'm out of my time, some conclusions. We find that offline fine-tuning is a very promising building block for continual learning. It's fast and requires very little data. It's simple, it's offline, and it barely differs from regular training. And you can do it repeatedly in a continual learning setting with virtually no performance penalty. Finally, I'd like to thank my collaborators and the workshop organizers for having me today. If you'd like more information, you can visit any of these links. And please